Hi, I'm Ferris of Logicoma. First of all, thank you for coming to this talk. I put a lot of work into it, and I really appreciate that the revision orgas are willing to still have seminars, even with this different format. So thank you guys for all the hard work you put in and the ability for us to record these talks and give them to you guys. I really appreciate that. Now, we don't have a terribly large amount of time to talk about what I'm going to talk about. There's a lot of complicated stuff here, and maybe not that complicated actually, but there's just a lot of stuff that I think people in the scene are a little bit less familiar with on the whole, seeing as there's a lot more demos than there are compressors. So we've got a lot to get through, so I'm going to go fairly fast, but we'll do our best to explain everything in as much detail as I hope is necessary, and maybe not too much, but we'll see. I'm Ferris of Logicoma, and I make 64Ks. So if you guys have never seen a 64K before, you might actually wonder what that is. So we'll do a quick overview. So 64K is a demo, so it's real time like all the other demos you've seen, but it fits in 65,536 bytes. Usually a bit less because we're a bit lazy. It's a single executable, so there's no external media. You can see in my little Explorer window here, the size of this particular one is exactly that size. And I think it's the coolest demo scene category. I mean, of course, I'm a little biased because I've been focusing on specifically making 64Ks for the last 5 years or so with the group Logicoma. And I think it's really fun, and I think we've still got a lot of room to explore things and grow, so I'm really excited for what the future holds as well. And hopefully, with the tool I'm going to be presenting today will kind of help push that forward as well. So this is what a bunch of 64Ks look like. Some of these are ours, some of these are from other groups as well. It's really great stuff here. 4 of these use Squishy because before revision last year, actually nobody used it since it wasn't in a state where anyone could. But after that, people started using it, and maybe I actually don't know if there are any intros from this year's 64K compo that used it. At least no one contacted me about it, but I did release it a couple weeks before the party, so I guess we'll see. So what is Squishy? That's the tool I'll be presenting today. So Squishy is our executable compressor. It's been developed since 2016, so shortly after our group started, really. It's been specifically built for 64K, so it has a heavier compression engine than you would find in like a 1K or 4K or 8K compressor. Which we pay for in size, but of course it works out in the end because we're able to compress a bit better. You can find it at this link. There's also a Poet page about it. So if you like it, let me know. And I'd really appreciate it if I could keep track of who's using it just for my own benefit. And also send me uncompressed executables because that helps me improve the packer, especially against your data, which I think should be beneficial for you guys if you're actually making 64Ks. So this is just a really basic high-level overview of what the 64K flow kind of looks like. We take some scenes and some shaders and some meshes. We stuff those through our demo tool and package that a bunch along with our synth code and player code. Out of that, we use Rust, so this is the Rust compiler, and out of that we get an intro executable, which is usually around a few hundred kilobytes. And then we stick that through Squishy, which is our executable compressor. And out of that, we get the actual executable, which is usually below 64K. Sometimes it's a bit more, and we have to work at that. But yeah, that's kind of the idea. So is it good? I'm just gonna get like this performance stuff out of the way. This is some stats versus where we show a couple things. So there's a lot of information here, so I'll go over this really quickly. But these blue bars are the final size output from Squishy. These red bars are the final size output from another tool called Crunchy, which is the sort of state-of-the-art packer for the last 10 years. There's also this yellow bar, which is the section size, which doesn't make too much sense yet, which I'll get to later. And then the green one is the section size from Crunchy. So in general, you can see that Squishy performs a little bit better than Crunchy. In some cases, this is a few kilobytes, which is like an entire 4K that you could squeeze into your 64K in addition to what you had before. And in particular, for our 64K that won revision last year, which is called Dope on Wax, this was actually about 3K smaller. And if we had packed that with Crunchy, we wouldn't have been able to fit. So pretty helpful tool. So yeah, it's pretty good. It could be better, which is something that, of course, I'm always working on. And I think the release version of Squishy, I called it version 0.1.0 because there's a lot of experimentation, a lot of fun things that I want to try. So we'll always be working on this. But yeah, so far it's pretty good. So before I talk to like the meat of what I really want to talk about, which is the actual compression, because that's mostly what I focus on with Squishy, we have to talk about what it's like to compress an executable. So I mentioned in that flow that what we take in is a working executable, and we have to produce a working executable that's smaller. So we do some compression, but we also have to do some other stuff here. So I'm going to maybe go a little faster through this part because it's the part that's less interesting for me, but I think it's necessary to talk about when you talk about an executable compressor. So yeah, that's what those slides said. So the whole point of this is we take an executable that works, and then we have to produce another working one. And this is different than when we normally compress to like a zip file or some kind of other archive, where we take whatever files on disk and then we store them into whatever kind of archive format that we would invent. Because the OS still needs to be able to execute it, there needs to be certain things at certain places in the file so the OS can actually load it and can understand what's in there. So we can't just compress everything. However, most of the data that the OS might use, actually it won't use, so we can get rid of a lot of stuff that are normally in an executable. For example, like debugging information and stuff like that, we will never need for a released intro anyway, so we'll just get rid of all that. And then we can also kind of fold and overlap some things. Now, an executable will also need to like import functions, which we'll talk about a bit later, and also there's these things called resources, which I'll talk about as well. So this is like a really, I know this is a very dense chart, but this is like a really high level overview of what's in an executable. And just going through this, so this is like where the executable file starts in memory. There's a little DOS program actually, and then there's a couple headers and some offsets. In particular, this offset points to this actual Windows specific stuff. And there's a lot of these kind of headers, just a bunch of header information, and then eventually you'll get to the stuff that's actually executable, which we'll talk about in a minute. Now, I blackened out the parts that are basically not needed. I think there's a few more fields in here that are basically never used. And a 1K or 4K or 8K compressor is going to try to stuff a lot of data into this. For 64K, we usually trade off a bit of compatibility. Or rather, we trade off a bit of size in that regard for compatibility. So since 64K is actually fairly large, we can usually afford to keep most of this stuff as is in order to make sure it's more compatible with future versions of Windows. Whereas, because a new version of Windows might come out and then suddenly one of these fields that wasn't used might be used. So we don't want to disrupt anything if we don't have to. But there are a lot of these things that we know our executable will not use. So we'll just kind of ignore them. And then we'll rely on our heavier compression engine to kind of make up the savings that we lost from doing that extra header packing. In 64K, that tends to be a better trade-off because we can afford to give our users a bit of a better experience by not letting a future version of Windows break their executable. But yeah, so anyway, this stuff is basically not needed anyway. And at the bottom here, we actually have something that's a bit different. So most of this is header information, but at the bottom of this is actually a section header, and this happens per section, right? So what is a section? So if we look at the image another way, this is actually kind of flipped. We have the headers at the bottom, and then this would be like the file on disk. So we have the headers, which is basically what I showed you in the previous slide, and then we have the code and the actual data that make up this particular executable. And these are laid out in different sections. And normally, when this is loaded into memory, these are actually loaded into a different offset in memory. And the code is built so that it executes as if everything were as it's laid out in memory. But then on disk, because there's some padding here, they usually can get away with aligning it a bit differently to make the executable file smaller. And this has nothing to do with compression. This is just normal executable stuff. And the alignment restrictions are there because you might need like memory protection. Like if this contains code, you don't want to be able to write to it. And you also don't want to be able to execute data. So there's usually alignment restrictions there. Usually these need to be at least aligned to a page. And then the image itself is going to be loaded to a particular offset. So anyway, the point is that there's these sections. And each one of those sections normally contains a header. But we want to be able to avoid a lot of that. Basically, we don't want to repeat this for every section that we have. So one of the most important things that we do is we actually sort of simulate that the whole thing's being loaded into memory, and we basically we simulate that everything's going to be loaded into memory. And then we actually stuff that into a single section that contains all of this, including the gaps. So yes, there are gaps there. We end up with some empty spaces, but since we're going to compress this anyway, this ends up being okay. But this way, we're able to get rid of some of those bigger parts of those headers, which are those section headers. Now, EXEs on their own don't do much that's very interesting. They need DLLs or whatever other system library you have for a particular platform. Of course, we focus on Windows because that's where the largest audience is. But they need DLLs to do all the fun stuff. And so you need like system APIs to actually create a window to display stuff on. You need graphics APIs to actually display your content. You need sound APIs to play some music. And the way that this works is there's this thing called imports that's also in an executable. And the imports contain a bunch of DLL names, so all the DLLs that your executable is actually going to load. And as we know, graphics APIs do everything for you, unlike the old DOS days where you were super hardcore if you did everything yourself. And, Anyway, so there's D3DX Spikeball, for example, which is a real DLL. Go check it. Geolutin free, also real. Totally check it. Totally believe everything I say. And then, so yeah, the point is there's a DLL name, and then there's also all the names of the functions as strings of all the functions that you actually import and that you're going to call. And these strings can be really large. So there's some common ways to get around this. Basically, we want to avoid using the actual executable mechanism, which has very particular table layout for all this data. And instead, we want to store it in some internal layout. And then before the code executes, we're going to do our own import code. So a common method used by like 1K and 4K compressors is called import by hash. So instead of storing all those strings, we actually store hashes of those strings. So like you could take a 12 character string and hash it down to 4 bytes, for example. And then what you'll do is you'll walk the system DLLs manually and hash the strings that are in those DLLs and compare them to your hashes, and then use that as a match rather than a full string match. There's kind of a chicken and egg problem here, which is how can we walk the system DLLs without loading them? And there's a way around this where we basically walk some internal structures in what's called the process environment block in Windows, and then we're able to get an offset to where the kernel32.lib, or actually that should say .dll file starts. But of course, these structures can and do change between versions of Windows. So again, for compatibility, we kind of want to avoid this. But if you have that, you can get load library and then go from there. You can also have hash collisions, though. Usually you'll use not a great hashing function in order to keep it small. So that's kind of two problems that we would like to avoid. So for compatibility for 64K, we actually do it more safely. We don't want to have a solution with collision risk, and we also don't want to do like walk opaque structures that might change between versions of Windows. So what we do is we use the standard executable import mechanism to have the Windows loader give us load library A and get proc address from kernel32. And then we will compress the library function names and strings, and then ordinals in case we use that. And then we resolve at runtime using those functions. So this is really safe and really straightforward. And then it compresses fairly well because we just compress the strings as is. And they're usually pretty self-similar. We also have what are called resources in executables. And these might be icons, which are kind of nice because if you want to like view your executable in Explorer, it's nice that it has an icon, it isn't just a name. And it also has things like these dialog boxes. They're also stored as resources in the executable. And the way the Windows API works, I don't think you actually have the option to just store these in disk somewhere. You need to be able to have this. You need to tell user32, I think is the library, to load this from a particular or from your executable image. So it has to be available from basically via the normal structures. Now, the interesting thing about this is that these actually need to be stored uncompressed, because in order for Explorer to actually get into it, it's not going to run any code from your executable. It's just going to walk some structures in the headers and find this data so that it can show those. However, some of these resources, for example, dialogues, they can be compressed because they're only ever going to be walked by the Windows headers or by Windows at runtime. So we can actually put the data for some of these in part of the compressed data that we do. And then we leave the other ones just kind of on disk as is, and just kind of rebuild the structure so that some things point into different places. There's also like manifests that need to be available uncompressed, but if you have a manifest in your 64K, you might want to look at your build settings. Anyway, so that's kind of it for generally the things that we do. Now, I know this is a bit confusing to visualize, so I actually wanted to do some kind of diagram about what it looks like when we actually pack up the executable. So this is kind of a visual representation of what the tool does. So again, we take the original image and then we simulate it that it's been loaded into memory. And then we take this upper part, which is the code and the data, basically all the sections that we know the intro will actually need to run, and that's called the image. Now, we will actually post-process some of this stuff. So, for example, the code, we're going to end up compressing with some x86-specific stuff, so we add some tables for that. We're also going to filter the code to compress better, and so we need to do some fix-ups there. And also the imports I talked about earlier, we need code added for that at runtime too. So we kind of stick some of this additional stuff underneath this section. I'll talk about why it's underneath as well a bit later. So then we end up with the image that's kind of been augmented with some additional code and linked in. And then we do what's called the big squish. So if you run Squishy, you'll see it does a big squish, and this is the really heavy part. This is what takes most of the time. And then there's also a small squish, which we'll get to. So the big squish takes this whole thing and then compresses this. And this does most of the heavy lifting. This is a very heavy compressor, which I hope to spend most of the time in this presentation talking about. And then after we have that compressed image, it looks really tall and kind of dumb, but that's because we need to put this after where the original image was. And this is where the decompressor for this compressed part is going to be added to the image in memory. We don't actually add it there because, first of all, we need this file to be small. So you'd think we would just add it above the compressed data, for example. But there's a reason why we do it here, and that's because we're actually going to compress this again. Our model is somewhat heavy, and in order to make it smaller, we actually add a second compressor stage, which I won't talk about much today because it's pretty straightforward. But that's what we actually do. So that's the small squish. Is we're gonna place the decompressor here in memory as if it were going to be uncompressed, and then we compress it. And then we take that compressed one and we stick it above everything here. And then we also add a bunch of stubs, which is like the code that actually invokes all these decompressors and everything, and some more header information and stuff. And then that's what we call the compressed image. So we put that all into an executable, which is behind me, but you're not really missing much. Then we output that executable, and usually it wins a compo, but that's up to you guys who's actually using this. So unpacking works basically the same way. So this is the final executable from the last slide, and then the Windows loader, when you double click this, is actually going to load this into memory. And then we tell, actually in the headers, we tell that the original entry point of the executable is not where it was originally, but it's in our stubs. So Windows will start executing in the stubs, and that will, of course, decompress this compressed decompressor to where the decompressor is up here. So that's what's happening there. Once that's done, it will actually jump into this decompressor and start decompressing the compressed image part. And this is where the heavy stuff works. Now, this is actually why I put this stuff under where the code and data. So the code and data is going to be decompressed into here. But of course, it's going to compress in order, or decompress in order. So it's going to decompress our fix-ups in our x86 tab as well. And this is actually important because once it starts decompressing the code, it's going to use some x86 specific tables in order to do that. And if we compress the x86 tables below where the code is, we can actually have those as part of our compressed part, but then they'll be decompressed and ready to use while we decompress the code, which is a pretty nice savings for this approach. And then eventually it will go through this empty space, decompress that, and then decompress this data, and then it'll be finished with that decompression stage. And then it will jump into where there's these fix-ups, so it'll do your imports, it'll unfilter the code a bit, and then finally it will jump into the original code of the executable. And you'll notice that this is roughly equivalent to what the original image would have looked like before any of this compression or anything. Mainly that the code, the data, and like BSS and some other sections that I didn't mention here are where the code expects them to be. And then we also have headers that are in a different place, but at least they're constructed accurately such that Windows can use them if it ever needs to like look for a dialog, for example. So as long as these are roughly equivalent, we're good and we don't have to worry about that. So that's kind of our job. So that's about it. I mean, there's really nothing super advanced or innovative in Squishy. So I don't really have that much else to say. But the point is we don't do very, very much advanced like header packing. It's 64K. Like we don't have hash import. And again, we make these trade-offs because we want the user to have kind of a better experience. But also in terms of like bang for buck, like to me, it always made sense to focus mostly on the compression engine itself to get better compression anyway. So we kind of make up a lot of those gains anyway. Another thing, like we actually make a similar trade-off for our synths, for example. So like it's usually smaller to kind of pre-calc music into a big buffer, but because we also have heavier synths in 64K, it actually makes more sense to pay the code size for like a multi-threaded player and have that play real time so that the user doesn't have to wait for the whole thing to load as long. But some of the stuff I might actually add as options later. We'll see. All right, so now we get to compression, and this is where kind of most of the stuff I want to talk about is. And the idea here is I want to get to where I can talk about the actual compression engine in Squishy, but we've actually got a lot of ground to cover before I can really explain that. So I want to kind of give a little bit of a 101 intro. I won't be able to go into as deep detail as I would like, but we're gonna do what we can. So as I mentioned, there's two compressors in Squishy, and they both have these kind of statistical components. I'll get into what that means. I only really have time to talk about the big one, which is the big squish. But everything I'm going to say actually applies to both. So when we want to compress something, we need to start with what we call a symbol alphabet. So this is just some terminology. If we're going to compress bits, we're just going to have a symbol alphabet that contains 0 and 1. If we want to do bytes, it's 0 through 255. And it could be ABC, it could be red, green, blue, it could be cat, dog, mouse, could be anything. And we construct a string out of the members of those sets. So AABC, for example, if we use this last alphabet here, we could make the string AABC. So it's any combination of these, and they can repeat. And there's order here as well. Now, since there's 3 of these, let's say we would do like a normal sort of uncompressed encoding of these. Since there's 3 of these, we could round that up to 4, and then we could use 2 bits per symbol, for example, and then this string would take 8 bits in this particular representation. That's hypothetical, but that's kind of the point here. So the point about compression is we want to find a new representation of the same string, which requires fewer bits but conveys the same information. So that sounds great, but like how do we do that? And we do that with stats. So the first thing we'll do is we'll construct a model. So most real world data contains what we call statistical redundancy. So basically some symbols are more common than other ones. And we can exploit this by making a statistical model of the string that we want to compress. So just as an example, we can take that same string, AABC, and we can just determine the frequency of each symbol within that string. And that literally just means to count them. So how many A's are there in this string? Well, there's 2. And then B and C each occur only once. And then we can take from those frequencies, we can determine what we call the probability of each symbol. And for this, we literally just divide the frequencies by the total string length. So the string was 4 characters long, so we'll just take those frequencies from this last slide, 2, 2, and 1, and we'll just divide those by 4. So for A, the probability ends up being 1/2 because half the symbols here are A's, and then B and C, a quarter of the symbols here are B and C. So that's kind of this model. And it's important that these are normalized, which we'll get to later. I don't know if I'll ever actually explain that, but just remember that. So then from that, we actually have a model. So our A has 1/2 probability, and then B and C are 1/4 probability in this simple example. And the point of this is just to show that like the model basically just has to deal with the stats of the actual data. So once we have a string and we have a model that hopefully matches that string, in this case we know it does, then we need a coder. So now I don't mean this kind of coder. We need to take a quick aside before I explain what kind of coder we actually do need. So this is Claude Shannon. Look at that hot piece of man. Claudia with a chance of meatballs over here did this really cool thing. He actually did a lot of cool stuff, but the thing that we're interested that he did is he came up with something called Shannon's source coding theorem, which states that the optimal code length for a symbol, notice that I'm using terminology I just showed you guys, is negative log 2 of the probability bits, where P is the probability of that symbol, as discussed earlier. Looks a bit complicated because logarithms are scary, but it's not that bad. So what this says is that the optimal code length for a symbol is negative log 2p bits. And then we have this model that says what the probability is for each of these symbols. So we can actually calculate how many bits each symbol should take in an ideal representation, an optimal representation. So for A, we take this probability, which is 1/2, we stick it into this formula, and we get 1 bit. And for B and C, we get 2 bits, right? And so from this, the job of the coder, which is what I'm trying to introduce here, is that it will code the symbols that we have based on the probabilities that we have, and it will always use the optimal number of bits as calculated above. Now, in practice, we have something called coding loss, which means that nothing ever gets exactly optimal. I mean, in some cases, it actually does. I'll show an example here where it actually does, but in many cases, we'll actually lose a bit. But at the end, we will approach this optimum. That's kind of the idea. So again, from this string, we're gonna define sort of what I would call the coder interface. So this would be, I don't know, some made up language where you can make a class. So a coder has an output string that it's gonna output bits to, and it has this encode method. And the idea is that you give it a symbol and a model, and it will maybe output some bits, maybe not. And the idea is that we're gonna invoke that for every one of our symbols in order and give it our model, and it should give us an output bit string that matches what we expect. So in this case, if we just take like some kind of hypothetical coder with this model and the string that we have, we're just gonna give each symbol in the string to the coder. So in this case, we give it A, and let's say it output a 0 bit. Then we give another A, let's say it output another 0 bit, and you'll notice that each of these little outputs that it produced are single bits. Now for B, as we calculated earlier, this should take up 2 bits based on its probability, and so then this particular coder might have output 2 bits, and then it does the same for C. Now notice that each time it outputs something, it actually output a unique code for each symbol. So it would be able to decode this, but the more important thing is that it actually output the optimal number of bits per symbol, and it was able to come up with unique strings for each symbol that actually matched that probability. So this comes out to 6 bits, which if we had worked this out earlier, this would have made sense. We'd have had a bit for A, 2 bits for B, and 2 bits for C, and all that together is 6 bits. So this works, and the whole point I'm trying to show here is not how a particular coder might work, but that it's totally possible to get coders that give you the optimal number of bits, and that's kind of the job here. Decompression would work kind of symmetrically to this. I won't spend too much time on that. But again, a general statistical encoding algorithm for compression is kind of what I'm trying to show you guys. So we have a model that determines per symbol probabilities for a given string of symbols. And then we have a coder that should, given those probabilities and some symbols in the string, it should encode those symbols with a number of bits determined by the probabilities from the model. And a really important thing here is that this model and the coder are completely decoupled. Now, there are many kinds of coders. The one that I showed here was a prefix code implementation. So if you've heard of Huffman coding, that belongs to that family. Now, this has some limitations. In particular, it was always doing per symbol replacement. It was always outputting bits whenever we gave it a symbol, and it was always outputting a fixed number of bits due to this direct symbol replacement. And real-world probabilities are often not powers of 2 like we saw here. So it was 1/2 and 1/4, and those are both powers of 2, negative powers of 2 in particular, which is why there's the negative in the log. But if let's say we have that same alphabet ABC and we constructed the string literally ABC, then each of the symbols would have a 1/3 probability. And if you work all that through the source coding theorem equation, you get this 4.75 bits plus or minus a little bit more. And of course, that's not a whole number of bits, right? Now there do exist coders that output fractional number of bits, and the way that they work can be summed up by the coder. It doesn't always have to output bits right as you give it symbols. You might want to flush it at the end, for example. And kind of one of the reasons you decouple it is you enable it to store maybe some internal state. And if it stores some internal state that represents some of those fractional output bits, then what you can do is you can say, let's say that there was a symbol that should be represented with 1/10 bits, so 0.1 bits. And then you tell the coder to encode that symbol 100 times. Well, that's fine as long as the coder output 10 bits. Then it works out. So with averages, you can kind of get it to, like, it never actually outputs fractional bits, but it's able to know that it doesn't need to output symbols all the time. And as long as the decoder agrees when presented with the same, with that output bit stream and the same probabilities, it will be able to reconstruct this stream. So it's actually pretty cool. So I really wish I had more time to talk about some of this stuff, like especially how asymmetric numeral systems work. Spent a lot of time trying to understand that, but we don't have time. But just again, the point is we have this model coder paradigm, and they're completely decoupled. So the other thing to understand is that the coding part of this is actually pretty well understood, especially when we're working on like maximum compression. We're going to have a pretty heavy model, and we're going to spend most of our time working on that. So a lot of the advancements in coders recently has mostly been biased towards speed. So we're actually using ideas that are basically 10, 15 years old at this point, but that's still where the best compression is. So that's what we're going to be doing. And the coder is not really so much a part of that. There is some precision and some other things, so it is useful to experiment with this stuff, but basically it's not the most important part. So Squishy uses what we call a binary range coder, and it has good fractional precision and is pretty fast. I experimented with some other stuff, but this is what I ended up with. But again, modeling, as it turns out, in contrast to coding, is a totally unsolved problem. It can be, in the example I showed you earlier, it was really easy to count symbols, and we'll see that that's not always the case. So this is where we get into some of the meat of the talk, where we actually talk about modeling and what to think about when you're designing a model. So getting a model right is really hard. It requires a lot of knowledge of the data, and 64Ks in particular can contain a lot of different kinds of data. So we need a really good general purpose model that needs to basically handle anything. And maybe it's a bit tuned to like shaders and text, because that's what a lot of 64Ks contain nowadays, but it also will contain a lot of like binary music data and stuff. So it needs to be general purpose. But one thing that they all have in common, at least right now, is x86 code. In the future, that might be x64, but right now it's x86. So we actually do have specialized modeling for this in Squishy, and I tried not to for a really long time, but it turns out it's totally worth doing this, and it's very important. So In the previous examples, we can start classifying the model that we saw. So we saw a ternary static order 0 model. So ternary means that there were 3 symbols in our alphabet. That's all that means. Static means that the same model was used for the whole string. So the model never changed as we encoded a whole string. And then order 0, we'll get to that part. So Squishy has what's called a binary adaptive context mixing model. So binary means there's 2 symbols. We're going to work with the whole stream as just a big stream of bits. And this is for speed and simplicity, as we'll get to a bit later when we start describing how the models work. And then it's adaptive, which, again, we'll need some explanation. So many files, again, especially intros, can contain all kinds of different data. So as we're going through the stream of bits, we're going to see some music data, we're going to see some shader data, all kinds of stuff. And our model should be able to adapt to the fact that statistics of these different kinds of data should change throughout the data, and then we'll achieve better compression. And there's some other advantages too, but that's kind of the most important part. And then this context mixing things means we're actually going to run several models instead of just like one model, and then we're going to mix many probabilities from those models together. And there's a lot of different names for this. Context mixing, I actually think, is a bad name because you're actually mixing more predictions than context. So I'm going to put that out there, but this is the standard name. And if you look up context mixing, you're going to find all the good information about it. So the reason why we do this is that we can build different models that are good at finding different kinds of patterns in the data. And so we want to run several in parallel to be able to kind of see as many patterns as possible. And then we're going to mix those somehow, mix their predictions and their results. This kind of context mixing model in particular, and actually in particular binary adaptive context mixing, this kind of model is used in a lot of top performing compressors, probably most notably the Pack family. And in the demo scene, there's like Crunchy and Crinkler that use this as well. Crinkler's based on some older versions of Pack. Crunchy's actually based on the same version of Pack that Squishy is. There's also some newer ones like CCM and CMix, but for the most part, we have to kind of strike a balance between maximum compression and also compression performance, because this needs to be able to decompress when the user double clicks the intro before the dialog comes up. So speed is actually pretty important. So we use some older ideas. Some of the newer ideas either give us better compression for way too many CPU cycles. For example, a lot of the deep learning ideas, they actually don't even offer better compression in my own tests, but they use way too much CPU cycles. So we need to kind of approach this somewhat minimal design, but yeah, so anyway, a lot of these ideas are like 10, 15 years old, but that's still the best that we have. So it's a really good strat, but it's also very slow. Like you don't see a lot of these ideas go into, for example, 7-zip or Kraken or some of these newer compressors that were designed especially, or like LZ4 that were designed specifically to speed up decoding. And that's because while they give really good compression, they are pretty slow. So often the trade-off favors speed a little bit more. But since in 64Ks, our uncompressed executable size is only a few hundred kilobytes, that's actually fine. So we'll just do something really slow anyway. So before I move on, we kind of have to discuss what is a context. And when I was learning about compression, I think this is what confused me the most, because it's kind of an abstract idea. But context represents local stuff kind of around a symbol. So I think earlier I showed that we just stuff symbols in order into the compressor. But we can generally do better. So the idea is that it modeled each symbol the same, the model that we had for the entire string, which is what we call an order 0 model. So to demonstrate this, we can kind of consider an English sentence, which is the cat kicked the dog in the face. So pretty likely sentence that a compressor will encounter. And an order 0 model doesn't care about like the placement of the words or the words in relation to each other. It only cares about, for example, how many times does the word the occur in this string, if we assume our symbols are words. And that's exactly the example we showed earlier. So this same string, or if we take a different string with the same symbols, so for example, cat dog face kicked in the, that's exactly the same words, but just put in a different order. And the same order 0 model, if we construct an order 0 model where we just count frequencies and probabilities of single words in context of the whole string, we would actually end up with the same model. Although this is a very different sentence. We know as humans that this is pure nonsense. And so what that tells us is that context actually really matters. So it's the words around the symbols around the symbols we're encoding is actually very important, not just this sort of global statistics. And I think you can already kind of maybe imagine why modeling is hard now, even just from that simple example. So just to stretch this a little further, a better model would give nouns, for example, cat, dog, and face, a much higher probability if the previous symbol were the word the than if the previous symbol were something else. There's a lot of other ways that text can be modeled that are based on this, and binary data also follows a lot of similar rules. But if we make stats that are based on what the previous symbol is, then as you can see here, a context that includes one symbol before the current one, that's called an order 1 context. So if we had no sort of local context, it's order 0. That's where that comes from. One symbol is order 1, and of course there can be order 2, 3, whatever. If you guys are familiar with Markov chains, I believe the term order in that context also means the same thing. And it can be order whatever, but of course as the order increases, then you're kind of looking at these strings, these of particular words in a particular order, and as those get longer, it's less and less likely that a given string is going to repeat more times. So we say that those contexts become more sparse as the order increases. And also, if you were able to store this in memory, these get really big because you end up having a lot of different combinations to store statistics for. So we need a good way to kind of deal with that. So how might we represent a context? So in the earlier example I used, I think we ended up with essentially like a hash map or some kind of map. We effectively want to capture substrings of symbols. So we could represent a context as a hash. So we take the last n bytes for an order n context, and we just like stick those in some whatever hashing algorithm, ideally a fast one. And then what that will give us is the hash is sort of a numerical representation of like after these n symbols or these n bytes, then we're going to see something. So what we can do is we can look that hash up into a table of model states. So the literally model state is states on that context hash. And then we can fetch a prediction from that model state. And then once we've actually encoded or decoded a symbol, we'll update the model again so it can adapt. Now, again, there can be many, many possible context hashes, especially as the order increases. So we want kind of an upper bound for memory usage. So we introduce something that we call a cache table. So first, what we could do is we could just do this direct mapping where a context might map to a specific model state always. Now, if you do this, you'll end up with like lots of collisions. It's essentially any times you might have a collision hash, a hash collision, you'll end up kind of mixing predictions for different things, and that generally hurts compression, and it can hurt compression like really badly. So Crinkler actually does this to make the code simpler. And as a consequence, they use a really, really large table in order to get less collisions, which is okay, especially if you're only compressing like tens of kilobytes of data versus hundreds. But again, in 64K, we have a lot more data. So an alternative is to use like an n-way associative cache. So each hash maps to n tagged entries in a fixed size table. And if no matching entry for a hash is found, we replace it with a new one. And so there's different, like with any cache, there's different like eviction strategies we can use with this. For example, LRU. And Squishy in particular uses a 32 megabyte 4-way associative cache table with LRU replacement. And the other thing is that we typically want to model many different contexts with many different models. And so the idea is like an order 2 context that looks at the last two words. We actually want to stick different kind of models to look at that same context. And so usually when we have a cache table like this, it's going to actually contain states for multiple kinds of models. And then we can also add models that work alongside the cache table if a better representation is available, because models can kind of be arbitrary history functions. But again, a thing to note is that a lot of the useful contexts are sparse. This is kind of an aside, but like you can have an order 2 context that doesn't look at the previous 2 words, but it might look at 4 words ago and 8 words ago. And this is actually really good with binary data where things are aligned on like 4 and 8 bytes. Then, for example, the byte that was 4 bytes ago and the byte that were 8 bytes ago might give you a better prediction than the 2 previous bytes. So these might be sparse, but anyway, that's just kind of a quick introduction into context. I know it might still be a bit confusing, but we got to move on. So yeah, our job is to build models that predict bits, and we use those to model our data in different contexts that we also build. So what kind of binary and adaptive models do we have, like a palette of things that we could play with? So another quick aside, we have to talk about how we represent probabilities. So first, I've been kind of assuming that they're real numbers, and real numbers constipate computers and make them sad. But we can use fixed point instead, which works pretty good, especially for binary probabilities. So with binary probabilities, when you only have 2, then it's actually pretty nice because you only have the probability for 0 and the probability for 1. And since there's only 2 and we actually know that they're normalized and that they sum to 1, we can actually only represent 1. So for example, if we model everything as the probability for 1, then the probability for 0 is actually implied. So we never actually have to worry about the other probability. We just update everything in terms of this 1 probability. And then what we can do to make it an integer is we can scale it by a power of 2. So instead of a real number between 0 and 1, we're going to have an integer number between 0 and 4096, for example. In this case, this would be 12 bits. And then you'll notice that this is not an inclusive upper or lower bound. So this is what's used in Squishy and Pack and Crunchy, and at least for final predictions that we mix and everything. But of course, many models might use more precision internally. So the first model that we could use to predict a bit is what's called a constant model or a constant model. And this will just output a fixed P1 with no adaptation, right? So for example, let's say it outputs 2048, then it's basically saying 0 and 1 are equally likely. So this results in no compression or expansion, is a really good way to test that your coder works. But it's not useful for much else other than mixer bias, which we'll talk about later, unless for some reason you have data that you can't model better any other way, and it is 75% zeros and 25% ones, then a constant model might actually be able to capture that. So this would be an example implementation, just as a probability function that just returns some kind of fixed number. We also have stationary context models, and these have two variables. There's a probability and a number of bits that have been seen. So the probability is the current prediction, which is usually initialized to 1/2. Of course, scaled if it's fixed width. And then the bit count is the number of bits that we've seen that we've modeled with this model so far, which is normally initialized to 0. And the idea is that there's the prediction, which just returns this prob directly, and then the update rule, which will take prob and it will bias it towards 0 or 1, inversely proportional to whatever the bit count was. The idea is that it will learn pretty fast initially and then eventually slow down. So this is kind of what the code looks like. Let's see. Yeah, that's basically, you're not missing much. Again, just bias the probability towards 0 or 1 depending on what the bit was, in order for you to predict better next time. And another important thing here is that this delta and this limit that we're in this are tunable parameters, and the best values of these are going to depend on the data. And in Squishy, we actually hand tune these based on how these models performed on our test corpus, and because everything's pretty adaptive, usually we can find parameters that work pretty good on everything, but I might actually expose those parameters in future versions. We'll see. But yeah, this initially learns really quickly, and then eventually it becomes kind of static. And eventually it'll kind of wiggle around a bit, but very slowly. And these are actually really good on, for example, text. This is also an example of what we call a direct model, which will output a probability directly. And so like a context maps directly to a prediction. But we can also make what's called an indirect model, and look at what kind of data that would be good at modeling. So an indirect model maps a context to a history. So we might actually have a few history bits that happen in the same context, and then we map that again to a prediction, which is why we call it indirect. So this would have like some counts and some last bits and a prediction table. And we also might share the prediction table between many models. It really depends on the data. But the idea is that we construct a table index by combining count, like how many times this has been used, or the counts of zeros and ones that we've seen before, and then whatever the last bits specifically were. Because we might have seen 5 zeros and 5 ones, but the last bits might be 1 0 or 0 1, and then we might be able to model that differently. And then we look at the prediction in the prediction table that we made from that table index. And we'll also use typically a nonlinear mapping, because the way that this logarithmic scaling works, then probabilities near 0 or 1, you usually want a bit more precision there to use, which just gives you better compression. And then for our update rule, we're going to update both the table entry and the model state. And a lot of the times you'll also, with this kind of table entries, you'll actually use a couple entries next to each other and interpolate between them and then update both. So this is kind of what the code might look like. Again, we return some stuff from a table. But the point is that we're not using a prediction directly. We're using some history that we've seen in this context to look up a prediction. Then we update both the prediction and the history. So over time, this can it basically just models different kinds of data than the direct ones. So this models repeating patterns in different contexts really well. So for example, this is a bit string, and if we break this down into chunks of 3, so this is the same bits, we're just looking at it a bit differently. Let's say we consider the end symbol of each of these 3 symbol blocks. If we assume an ordered order 2 context, the last 2 symbols are the context. And then after we see 0, 0, we can actually see that there's a repeating 0, 1, 0, 1 pattern here. So every time we've seen 2 zeros, we want to predict a 0, and then the next time we want to predict a 1, and the next time we want to predict a 0. And this is the kind of data that this indirect model is good at doing. So an indirect model with a 1 history bit will learn that if we saw a 0 in this context last time, 1 is highly likely and vice versa. And this kind of pattern, as you might imagine, is really common in actual data. So these models pull a lot of weight and squishy. They're very important. And things like the number of history bits that are included in the model, the prediction table size, the way you update parameters, all that stuff is tunable. So you could build many different kinds of variants of this kind of model. And again, in squishy, all of these parameters have been static and tuned on the corpus. And I might actually expose this someday, but we'll see if that's actually useful. So there's a lot of other primitive types of models that you can make. These are just kind of 2 examples. Some common ones are run models for long strings of the same symbol. So they'll store like the last symbol that was seen and how many times we saw it. There's also match models where these work better for sort of modeling higher order context. So like essentially you use these suffix hash tables to find long strings in your data. So you say, look, let's look at the last 8 bytes and where was the last place we saw them in the data. So you kind of have this rotating pointer buffer. And then from there, you can say, well, last time we saw these 8 bytes, this other byte followed, and then we can use that to predict. So match models are doing something like that. You can also have variable order models, which I'm not going to talk about at all because these aren't used as much anymore. But they were really popular in like the mid-2000s, I think. But the kind of point is that this is actually a fun place to be really creative when building a compressor and playing with different models. You really kind of get a feel for what's going to work and what doesn't. And in particular, the indirect models that Squishy has are a very different design than what all the different versions of Pack that I've seen actually use. And we were able to get better compression than a lot of those other models for more memory and more CPU cycles. But it was really fun to design those. So now we're going to talk about actually mixing the predictions and how that works. So we have loads of predictions that come from our models, and we want to combine them to perform a better prediction. So there's basically any way that we can do this we want. The predictions are these fixed point values from 0 to 4K96 or whatever. So as long as we take 2 of those and we want to mix them together, and then as long as we get a new number that's between 0 and 4K96 and that's useful, it's a valid way to combine these. So for example, linear mixing with fixed weights. So this is exactly what it sounds like. We take probability X and probability Y, and then we have this A. This basically lerp. And A is tunable. This particular model is not that useful as it turns out, because it basically says that one model is always better than the other. And then that bias is determined by this alpha here. But it's my point for showing this is, again, we can do a lot of different things. Like this is still a valid one, even though this one isn't particularly useful. You could do a weighted average. You could be really creative here. What Squishy does, and a lot of the more successful context mixing compressors does, is what's called logistic mixing. So the idea here is that we remap the input predictions on a logistic curve. So instead of a linear mapping, we get this kind of S curve. And again, this gives us more precision on the ends, as well as does a couple other things. And then what we do is we do a weighted sum of some of these remapped predictions. And then we remap that sum back to a linear domain and then use that as the prediction. This is basically a perceptron from neural networks, where we take a bunch of inputs and then we do this weighted sum, except we have a remapping function on the inputs and then the inverse function of that on the outputs. And it turns out this is really good. So this is kind of the neural network part of the model. And another really cool trick is that we don't always have to use the same weights every time we mix. We can actually use a context and select different weights here. And that actually is a really important way to use this that also compresses really well. So some other loose ends about modeling and mixing. We have a lot of freedom to mix and match and adjust predictions. But in addition to that, we can also do things like post-processing. So after we mix, we can also do something called secondary symbol estimation, or adaptive probability maps is one like implementation of that. Where once we get the final output, we might put that in a table that might map to a different prediction and kind of adjust that, so that whenever the model is really confident it's going to be 1, let's say every time the model is really confident it's going to be 1, we actually tend to observe zeros, then this kind of probability map can kind of learn in what ways the model tends to be wrong and be able to make up for that. Just like where we had direct and indirect models, you can do the same thing with the secondary symbol estimation idea. where some history and some context can also map to another entry. So all kinds of stuff. We can also do multiple mixer stages, which is really successful. And you can also enable and disable models for different data, which is actually also quite effective. So now we're finally going to get to the actual architecture in Squishy. And I think that the architecture is actually a lot more straightforward than it might sound, but does have some crazy ideas. So I think it's fun to talk about. So essentially, the Squishy model architecture is mostly based on Pack 7, but it has very hand-tuned models. So versus the models that are in Pack 7, there's kind of increased precision everywhere. The design is not too much different. It's mostly based on like ZPack. But there's a lot of other kind of enhancement ideas, but it's mostly just more precision on the same kind of ideas. And as I mentioned earlier, like there's a custom indirect model design that's just playing around with this stuff, as I mentioned. So there is some special x86 stuff, which I'll get to later in its own section in the talk. Now in 2017 and 2018, I was actually, I actually focused on like this VM where you could actually describe different models as little opcodes and then have it run that. And I actually built a working version of Squishy that did that at runtime. And it turns out it wasn't that good because first of all, the architectures that I was playing with weren't that good. And also, of course, the decoder is quite large when it has to interpret all those opcodes. But a cool thing about this is I was able to use a genetic algorithm to kind of grow different architectures and play with a lot of different ideas. But I never really reached a good performance. And there's a few different reasons why. For example, I didn't really understand the multiple mixer weight context ideas, which again, I'll talk about. And the models weren't as good as they are now. So I might try this again in the future. But again, my point with this is that there's a lot of things you can try. And I did try a lot of things and ended up kind of going with a more classic kind of architecture. So I still want to experiment more in future versions, but that's basically it. So yeah, it's based on Pack 7 with hand-tuned models. So first we have a set of context models. Again, there's this single 32 megabyte cache table. And each entry, which is 16 bytes large, has a cache tag for the actual cache table structure. And then it has it has state for a stationary direct model, which is 4 bytes. It has state for an indirect model, which is another 4 bytes, where I think I use 2 bytes for the count, 2 bytes for bit history. And then I have, or maybe I distribute that differently. I honestly don't remember. And then I have a run model, which I mentioned briefly earlier as well. And so those are kind of the 4 bits of state. And so the 3 models there. This cache table is a 4-way associative cache. So each bucket is 64 bytes wide, which maps to cache lines, which helps with speed. So the whole thing is allocated on a 64 byte boundary. Now, because of those there's three different models per context. We model 21 different contexts used in the data sections. Again, we'll get to the code stuff. And the contexts that are actually selected are basically handpicked static descriptions, it's essentially a byte mask and a bit mask. So it's whatever the previous bytes were. There's up to 8 bytes. There's a byte where each of the bits map to bytes that we're going to include in the hash. And then in addition, there's also a bit mask that also masks all those bytes with a certain number of bits to kind of construct that context. And so each context is modeled by one cache table entry. So there's, again, 3 models and predictions per context. So what we do is we take the history stuff and we construct this hash. We look up in the cache table entry and then we run 3 models on it. So in total, with 21 models and 21 contexts and 3 predictions per context, we end up with 63 context model predictions. Again, in the data sections, because we do some more fancy stuff in the code sections. So in addition to those 63 context model predictions, we also add a const model, which is also hand-tuned. But again, it's just a constant that tends to work. And I don't know if I actually talked about this, but the main point about a const model is that when you're mixing these predictions with these weighted sums, the const model is really good as kind of a bias, because then the mixer, if the mixer suddenly finds that the model is always a little bit off by a particular amount, it can kind of, by expressing the weight on the const model, add and subtract a little bit of bias that wouldn't otherwise be able to do. So this is kind of just a nice way to work with that paradigm. So that's mostly why the const models are useful here. So there's a single one of those, and then in total, then we end up at 64 predictions. Now the numbers are starting to look kind of nice. And then on top of that, we run 8 match models, and each of these is, again, this rotating kind of history buffer. But each one has has increasing context orders for the hash that it uses for that buffer. And this actually does make more of a difference than I would have thought when I tried that idea. I thought it was kind of dumb when I tried it, but it totally works. And it's easy to add, because as soon as you have one match model, it's easy to put those in a loop. So in total, with all of that, we end up with 72 total model predictions. So 72 models that we run per bit of all the data sections. And then we mix those together with logistic mixing. So there's a first stage where we actually take all of those 72 predictions and we mix them 8 different times, which again seems weird. But each time that we mix those, we actually select different weights from 8 different contexts that we also calculate. So there's one static context, which basically uses the same weights every time. So that's as if you weren't selecting different weights. There's 5 byte history contexts, which use different orders. There's orders 1, 2, 3, 4, and 8. There's one that just looks at the bit history for the current bits, or the bits of the current byte as a context. And then there's this one context that I just threw together some stuff in that has a match model state and some other stuff. And the key here, when I was experimenting with this, actually seems to be that you want to mix and match a lot of ideas. It seems to be that for context, you want to, like if you think of context as where your model can look for patterns in the data, you want to have a lot of places that it can look. And then in terms of the models, that's like, I guess a good way to put this is with context, you endow your model with a lot of places to look. And with different models, you endow your model with a lot of ways to recognize patterns. And the combination of the two, you end up with this kind of weird matrix of features that should end up covering all of the things that you'll see in an actual executable or in whatever other kind of data you're compressing. So the key here is to mix and match a lot of stuff. So that's why we end up with like this weird context, for example. And this actually is really important. I think this was kind of the biggest breakthrough that I had when working on the entire compressor, was understanding this mixing stuff. I hit a big wall before I was able to understand that you want to actually swap out these weights and do kind of crazy stuff here. So you'll notice that since we mix 8 times, then we end up with 8 new predictions, and then we mix those with a second mixer stage that mixes those 8 mixed outputs, and that uses static context to use the same weights every time. So both of these stages, because we end up with, for example, 72 predictions in the first stage and then 8 in the second one, those are both divisible by 8. So we do 8 wide, 8 lane SIMD, and 16-bit mixing for all of that stuff. So not super fancy, mostly SSE2, which is old stuff. And I use SSSE3 for horizontal sums, but that's basically it. And that's basically the only SIMD that's used in the entire compressor. Additionally, after that, after all the mixing, there's 3 APM stages that are run in serial. And so this is just some kind of post-processing on the weight. These each have increasing context orders, and they're static linear weights. And the weights are actually quite low. So there's not a huge difference after all the heavy modeling that we've done when we apply the APM, but it still does pay for itself. It's cheaper to have the code for this and to do it than to not do it. So it pays off. So after that, we finally get the final prediction, and then that output is clamped in this 1 to 4095 range, and then we send that to the coder. But again, there's lots of possibilities. And this is what we've ended up with that works so far and performs really competitively with the other offerings that are out there for 64Ks. But future squishy versions, I hope, will do a lot of different stuff. I want to experiment with this a lot more. I think it's really fun. But that's what we have now. So now on to the x86 specific stuff. Again, I tried to avoid this, but to be competitive, I had to do this. So the first thing that we do is we have what's called an EA E9 filter. So these are the opcodes for jump and call. And in x86 code, those are relative offsets, which actually sucks, because if you want to call the same function in 5 different places, then where you call it from determines the actual offsets, even though you're calling the same code. So what you would think of as the same piece of code actually is encoded differently all 5 times. So we do a filter to change those I don't know why I lost the word here, but to change those, relative offsets to absolute ones, and that will help compression. And then we add a stub to undo that later. Now this will actually be replaced so that it'll work better with some stuff I'm going to talk about in a minute. But it does actually help compression quite a lot. But we need something more comprehensive than just that. So the main idea for x86 compression and squishy is that we actually leave the code in place. We don't reorder the code like Crunchy, if you guys have read about that, actually does that, because there may be useful correlations in the code as it is. And by reordering, we kind of force it to see certain correlations, which usually is better, but it might not be in some cases. So what we do is we run this on-the-fly state machine disassembly, and the picture that I'm showing here is one of the test outputs from that, where we have a bunch of instructions from an executable. And then you can see I've colored the different bytes here based on whatever the state was for this disassembler. And you can see it basically lines up everything nicely. So it's able to correctly enough decode the x86 here. And then what we can do is we can use that disassembly state as some additional context. So for example, we can select different mixer weights depending on what that state is, different indirect probability tables, all kinds of stuff. But we can also use this disassembly state to maintain different history buffers. So instead of just leaving the code as is, we can also make a bunch of history buffers that represent, for example, the last opcode bytes or the last displacement bytes. So it's almost as if we had actually put these different kinds of bytes in different states anyway, but in addition left those as is. And so then what we do is we double the number of context models that actually run in the code section. So instead of 21, we end up with 21 times 2 or 42. And so then in total, we end up with 135 predictions. So the first set of 21 contexts represent the data as is, and then the second set represents context, but only looking at the data in the current history buffer. So only the last opcode bytes or only the last mod RM bytes or whatever for x86 encoding. So yeah, so we end up with 135 predictions. And the nice thing about this approach is that we kind of get the best of both worlds. We see correlations in the in-place code, and we also see correlations in the sort of reordered code between specific bytes. Because the other thing is with x86, you can see all the instructions are kind of all over the place. These are all variable length, and doing it like this allows us to kind of work around that limitation. Whereas otherwise, if they were all fixed length, for example, then regular context models, I think would model that a lot better. So that's kind of the idea. It's a bit crazy, but it's not as crazy as it could be. Like we can actually mix and match histories in more arbitrary ways than what we do, which is kind of the main motivation between that failed genetic algorithm idea that I had. But it might still be interesting, so we'll probably experiment with that more later. Now, the other thing is this leads to a larger model due to this x86 specific stuff on top of an already pretty large model for all the heavy compression that we're doing. But what's cool is we can fold a lot of this into the main compressed state. I think I mentioned earlier that we have some like x86 tables that we put before the code in the compressed stuff so that gets decoded first, and then we're able to use it. So we actually take the code and the data and put it there for this model, and then we just never invoke that when we're not compressing the code section. So that actually works pretty well. Of course, this additional model logic in the history buffer code is still somewhat big, but this is why we have a second compressor stage on top of this, which again, uses a lot of the same ideas, but of course is scoped a lot down in order to make it small enough to put in front of this whole thing. So anyway, I know I went through a lot of this stuff and went through a lot of it really fast, but I hope that this was good. Some points, Squishy's pretty good. There's lots of stuff in this. This has been a big project for me the last 4 years. It's a very important part of our 64K tool flow. And I think a lot of authors seem to forget how much work actually goes into these. I know that when I've been making 64Ks with Crunchy, the Farbausch tool, that's something that I didn't think about much. But thank your Packer authors, guys, because this is actually really important. And I would also say, I don't really blame anyone for forgetting about that stuff, because I think it's a good sign of good tooling, because usually if you're using a tool and you don't really notice you're using it, like it's kind of out of your way, I think that's a good tool. But anyway, it's big. There's a lot of stuff here, but it's not really rocket science. It's a lot of mixing and matching ideas that I presented here, along with a bunch of others. And I think these are really fun to make. I would actually like to see more people make their own Packers in this scene. I think there's only probably a handful of people that really do this seriously, and I think that there could be a lot more if people understood a bit more about what it's about and what you should focus on. So hopefully this talk kind of inspired you rather than scared you. But if not, come talk to me at some party, and then we'll see if we can change your mind, because I think this is really fun. And of course, we're all doing this so that we can make more and better intros, and especially 64Ks. Again, that's my favorite category, and I would love to see more of them. So make more intros. But of course, if you're into 4K or whatever, do that too. Just make awesome stuff. It's really cool. Also, if you're making 64Ks, we have a synth that can help, but that's for a different talk. So yeah, thank you guys so much. This has been a blast. I know it's a lot, but I really appreciate you guys listening and watching. And yeah, I hope you guys enjoy the rest of our revision. Thanks a lot.